You already know what a raindrop looks like. That image is wrong. Not wrong the way a lie is wrong, wrong the way a map is wrong when it leaves out the territory that turns out to be the interesting part. The teardrop shape you picture, the clean vertical descent, the single drop tapping a window, none of that is what is actually happening. A raindrop falling through open air is oscillating, wobbling, flattening continuously into something closer to a hamburger bun than a tear. And at a certain size, it does something nobody fully predicted until someone levitated one in a wind tunnel and filmed it at 2,000 frames per second. It turns into a bag, a thin, hollow bag of water with a heavy rim of mass around its edge, inflating upward into the airstream like a translucent balloon until it bursts, not breaks, bursts into dozens of smaller drops, each one beginning the whole process again from a lower starting point. And the question of why this happens, which sounds like it should have a clean answer involving surface tension and drag, turns out to be the same question as why rain exists at all. That second part is the one I did not expect. There is a number, 8 million, I want to place here at the beginning and return to at the end. It is the number that cracked my prior assumption about how rain works. And it sits underneath everything in this video the way a foundation sits underneath a building you have never thought to question. You will understand what it means in a few minutes. For now, hold it. I came across this problem while looking at something else entirely, the way different raindrop sizes affect the accuracy of weather radar readings. There is a formula worked out by two researchers at McGill University in 1948, Marshall and Palmer, derived from measurements of rain falling over a Canadian summer in 1946. They stood outside with collection equipment. They counted drops by size. They fit a curve. The Marshall-Palmer distribution describes the number of raindrops at each diameter in a falling rainstorm. And its shape is a clean, decreasing exponential. Many small drops, progressively fewer large ones, the count declining smoothly as diameter increases. It is the kind of result that feels almost too tidy to be real. I was using it for a practical purpose and paying no attention to its implications. Then something stopped me. The distribution cuts off. There is a maximum size for a raindrop, roughly 5 millimeters in typical rainfall, occasionally reaching 7 or 8 millimeters under strong updraft conditions in tropical storms, and then essentially nothing larger. The distribution does not just thin out at large diameters, it disappears. I had accepted this the way you accept that the sky is blue, as a fact that arrived pre-explained, attached to some vague classroom memory of surface tension and air resistance. I thought I understood why raindrops. I assumed it was something clean, a threshold where one force simply overcomes another, already settled and filed away. I was not even close to the actual mechanism. The real explanation is more interesting in the specific way that problems are more interesting when they involve a competition between multiple forces, each with their own logic, rather than one force that simply wins at a threshold. I kept going past the point where I had a serviceable answer, because the serviceable answer kept opening into something more interesting behind it. The original radar problem is still in another tab I never returned to. The question I ended up with is harder than the one I started with, and I am genuinely not certain I have answered it fully. Closer to a hard question is not the same as close. If this is the kind of thing that tends to happen to you, one thread pulled, hours gone, the original work quietly off the screen, you might want to subscribe or not, but stay, because it gets genuinely stranger before it gets clearer. Here is what the standard explanation says, and I want to be fair to it, because it is not wrong. It is just incomplete in a direction most explanations never bother to explore. The first layer, the one almost everyone has heard, raindrops grow by collision and coalescence. They fall through a cloud, bumping into smaller droplets, absorbing them, growing larger as they descend. At some point, aerodynamic forces, the drag on the flattening lower face, the pressure differential across the drop, overcome the surface tension holding it together. And the drop breaks apart. That is the ceiling on size. True as far as it goes. The second layer, and this one behaves differently from the first and third in a way that matters, is that breakup is not a single mechanism producing a consistent outcome. It is at least 4 distinct physical processes, each generating a completely different distribution of fragment sizes. Filament breakup, where 2 drops collide at a glancing angle, briefly merge, then separate, leaving a thin water bridge that beads apart into small droplets while the 2 main drops mostly survive. Sheet breakup, where a more direct collision spreads the coalesced mass sideways into a horizontal sheet before one edge lifts in the airstream and the whole thing. Tears apart. Disc breakup, where a central impact flattens the drop into a thin wafer whose edges disintegrate outward. And bag breakup, which I will return to in detail because it is the mode filmed at 2000 frames per second, and the one that made me keep watching the footage far longer than was strictly necessary. I called this layer different from the others because it is not really the cause of the size limit in a simple sense. I included it because its complexity is what makes the limit hard to predict precisely. The absence of a single clean mechanism is itself the important thing. The third layer is the one almost nobody discusses when explaining why raindrops have a maximum size, and it is the layer this script is actually about. It is not about why individual large drops break apart. It is about why the entire population of drops across a whole rainstorm, billions of drops at every stage of growth, breakup, and evaporation simultaneously, self-organizes into a stable distribution with a consistent shape. A shape appearing in rainfall from light drizzle in Scotland to monsoon downpours in the Bay of Bengal. That stability, spontaneous and uncoordinated, emerging from billions of individual collisions with no organizing principle anyone has clearly identified, has a genuinely unresolved question at its center. That is where this ends up. Start with the problem that is not the one you think I am building toward. A cloud droplet is approximately 10 micrometers in diameter. A typical raindrop is approximately 2 millimeters in diameter. That is a factor of 200 in linear dimension. In volume, because volume scales as the cube of radius, that becomes a factor of roughly 8 million. A single raindrop contains about 8 million times the volume of a single cloud droplet. For rain to happen at all, each raindrop must aggregate the water from millions of cloud droplets. And this aggregation must happen in minutes, not weeks. That is the number from the beginning. When I sat with it properly, the whole mechanism of rainfall began to look improbable. How does that aggregation happen fast enough? Diffusion alone, vapor molecules drifting randomly toward a growing surface, would produce a raindrop in something like months to years under typical cloud conditions. Something else must be accelerating the process by several orders of magnitude. And identifying that something changes how you understand everything that follows. The answer is differential fall velocity. Different sized drops fall at different speeds, and that difference is what makes rain physically possible on the timescales we observe. A cloud droplet at 10 micrometers falls at roughly 1 centimeter per second, so slowly that any modest updraft keeps it suspended indefinitely, which is why clouds can exist as stable structures without immediately precipitating. A drop at 2 millimeters falls at around 6 meters per second. A drop at 4 millimeters falls at about 8. The largest raindrops, near 5 or 6 millimeters, reach terminal velocities around 9 to 10 meters per second, after which increasing drag from their flattening shape prevents further acceleration regardless of additional size. Philippe Lenard established this saturation effect in 1904 in a wind tunnel he built himself by increasing upward airflow until drops of known diameter became suspended. Suspension speed equaling terminal fall velocity. He found that fall speed stopped increasing past about 4.5 millimeters and attributed this correctly to the drops changing geometry, increasing aerodynamic resistance faster than mass was accumulating. He published in a German meteorology journal. Nobody paid serious attention for decades. He moved on, won a Nobel Prize for unrelated work in physics, and never returned to rain. Because larger drops fall faster through a field of slower, smaller drops, they sweep those drops up. They grow. As they grow, they fall faster, sweeping up more. A feedback loop, a runaway process with no obvious internal break, which is precisely why the question of where it stops is not as simple as it first appears. Here is where the geometry of falling water starts to matter in ways that go beyond intuition. And this is where it gets strange, not for researchers who have lived in this territory for years, but for you specifically because of what you now know. A drop below 0.5 millimeter is spherical. Surface tension dominates at this scale. The drop occupies the lowest energy configuration available to a volume of liquid, which is always a sphere. The ratio of inertial forces to surface tension forces can be expressed as the Weber number. Below roughly 12, surface tension holds the drop stably spherical, regardless of the air moving past it. Small drops live comfortably in this regime. Past about 1 millimeter, the pressure differential between the leading face, the bottom, ramming through air, and the trailing face above begins to flatten the drop. The bottom gets pushed slightly upward. The sphere becomes an oblate spheroid. It oscillates as it falls, cycling between more spherical and more oblate at a natural resonance frequency, like a bell ringing in its preferred key, damped by viscosity, still intact. Past 2 millimeters, the flattening is pronounced enough that Lenard's description fits accurately: a flat bottom and rounded top. Like a hamburger bun, the lower surface is nearly flat, maximizing drag. The drop is under increasing structural stress, internal pressure no longer symmetric between top and bottom, past 4 to 5 millimeters, and the exact threshold depends on updraft strength, air pressure, humidity, and the drop's individual collision history, not just its diameter. Something unexpected happens. The center of the lower face, instead of bowing gently inward, punches upward through the drop. The rim, containing most of the mass, stays outward. The thin central membrane stretches upward. What was a flattened sphere becomes a translucent membrane stretched across a heavy circular frame of liquid. Then the airstream catches the membrane, the center lifts, the bag inflates upward, thinning as it expands, surface instabilities propagating as waves until rupture becomes inevitable. And then it bursts. The membrane disintegrates into a fine mist of tiny droplets. The rim either stays intact or breaks into several medium fragments. One drop becomes dozens, some very small, some medium, none as large as the original, each beginning the coalescence process again. This is bag breakup. In the landmark 1982 collision study by Lowe and List, 25,000 observed drop collisions. Bag breakup appeared exactly 3 times, 3 events in 25,000. In later high-speed camera experiments, specifically targeting larger drop sizes, it appeared 13 times in 25 events. The reason bag breakup requires the very largest drops, which earlier studies had avoided because they were difficult to generate reproducibly. Once you work in the size range where bag breakup is physically possible, it becomes the dominant mode rather than a footnote. And its fragment population, fine, mist plus a few medium drops, is completely unlike what filament or sheet breakup produces. Different modes leave different fingerprints on the rain below. Now, I need to say something that reframes everything above. The breakup modes explain why individual large drops cannot survive. They do not explain why the collective distribution of all drops across an entire rainstorm is as stable as it is. And that stability is what I actually cannot stop thinking about. You are probably expecting this to start resolving. I thought so too. At about this point in the research, the curve was supposed to bend toward a landing. It did not. Consider what the atmosphere is doing to a falling rainstorm simultaneously at every level. At the top of the rain column, drops are forming and beginning to fall. As they descend, they collide. Larger drops catching smaller ones through the velocity differential. Both populations simultaneously growing through coalescence and fragmenting through breakup. Below cloud base, in the drier air beneath, every drop is evaporating, losing mass at a rate depending on local humidity, drop size, and velocity. Drops that began at 2 millimeters may arrive at 1.5. Some evaporate completely in descent, producing virga, the visible curtain of rain hanging beneath a cloud and disappearing before it lands. A phenomenon common enough to have a name and strange enough that it deserves one. Updrafts lift smaller drops back upward for more growth time. Turbulence alters collision rates in ways calm air models underestimate. Evidence suggests atmospheric turbulence enhances collision rates between similar-sized drops by factors the standard gravitational sweep-out framework does not capture. All of this happens across billions of drops with no coordinator and no global feedback. And yet, measuring rain at the ground, you find reliably something close to the Marshall-Palmer exponential. Small drops outnumber large ones in a consistent ratio. The shape appears in light drizzle and in tropical downpours alike. Rainfall intensity changes the scale. The shape does not change. Why? This sounds like a question with an answer waiting behind it. It does not have one, not a complete one. The Marshall-Palmer distribution has been described since 1948. A satisfying physical explanation for why it takes that particular form and why it is as robust as it appears remains genuinely open more than 70 years later. Two explanations compete. The first, the distribution is a true statistical equilibrium. Given enough falling distance and enough interactions, any initial size distribution converges toward the exponential form through coalescence and breakup. The way a gas with any starting velocity distribution converges to the Maxwell-Boltzmann form through molecular collisions. If correct, the Marshall-Palmer distribution is something like a law of nature at the scale, a fixed point the system finds regardless of initial conditions. Some simulations support this. Others do not reproduce the convergence cleanly, and the fall distances required may exceed what most real rainstorms provide. The second, the distribution is not a deep equilibrium, but a persistence of initial conditions. The drops leaving cloud base may already have an approximately exponential size distribution for reasons rooted in how clouds nucleate and grow droplets internally. If the distribution is already close to exponential when it enters free fall, what looks like convergence during descent may simply be a starting condition the physics of falling does not alter much. Same curve at the ground, completely different physical meaning. Here is an analogy that breaks in an instructive place. The raindrop population is a little like a market. Individual participants, drops colliding, merging, breaking, evaporating, are chaotic at the individual level. The aggregate is stable. In a market, stability emerges partly because participants carry mental models of equilibrium and act on them. The analogy breaks exactly here. Drops have no models. They obey local physics, one collision at a time, with no awareness of the global distribution they collectively produce. The stability that emerges without coordination or global feedback is precisely what lacks a fully satisfying explanation. In roughly 10 to 20% of measured rainfall events, particularly in intense convective storms, the distribution deviates from the expected form in structured ways the standard framework does not predict cleanly. The framework says it should not look the way it looks. It keeps looking that way. The word parameterization appears throughout this field's literature and is worth pausing on. A parameterization is what researchers produce when the underlying equations are too complex to solve exactly. You run experiments, fit curves to the results, and use those curves as stand-ins for the real physics in models that need to run at practical speeds. This is responsible science, not failure, but it is a signal. Description is ahead of explanation. Fragment-sized distributions from each breakup mode are described by empirical functions fitted to laboratory data, not derived from fluid equations. Coalescence efficiency is tabulated from experiment, not computed from first principles. The stochastic coalescence equation governing how the full drop population evolves has clean solutions only in simplified limiting cases. In the realistic general case, it must be solved numerically with approximations using kernels that are themselves experimentally fitted. The science predicts well enough to build useful weather models. It cannot yet write down an equation from first principles whose solution is the Marshall-Palmer distribution. That derivation does not exist. So I am back where I started, more or less. That number, 8 million cloud droplets aggregated into a single raindrop. I understand the mechanism better now. The terminal velocity differential driving the sweep up process. The 4 breakup modes and the conditions selecting between them. The bag inflating at 2,000 frames per second before it bursts into mist. A fragment population earlier literature had barely characterized because nobody had filmed drops that large in enough detail. The reason a raindrop stops growing is real, documented, and stranger than it looks from outside. What I understand less than when I started is the stability of the collective. Why the population of drops churned by turbulence and evaporation and updrafts and continuous collisions keeps settling into the same distributional shape across rainfall events that are otherwise wildly different from one another. Whether that shape is a true equilibrium the physics drives toward from any starting point, or a persistent imprint of cloud conditions at the moment precipitation first forms. Whether the 10 to 20% of deviating events are marking something fundamental about the limits of the framework. or simply the edge of the parameter space where the empirical fits were calibrated. Leonard built his wind tunnel in 1898, measured drop shapes with blotter paper dusted with dye, found the fall speed saturation, and identified instability above 5.5 millimeters. He published in 1904. Nobody read it seriously. He moved on and never returned to the subject. 120 years later, researchers are still running drops through wind tunnels, filming them at 2,000 frames per second, refitting equations to breakup distributions, and debating in journal papers whether the equilibrium raindrop size distribution has ever been cleanly observed in nature, or whether the instruments measuring it produced artifacts that mimicked what the theory predicted should be there. The question gets cleaner the deeper you follow it. The discomfort gets worse. A raindrop falls through 4 kilometers of atmosphere in roughly 7 minutes. In those 7 minutes, it participates in a system whose aggregate behavior we can describe accurately enough to be useful, and whose deep explanation we are still carefully working toward, without a clean arrival date. That is usually what happens when you follow something far enough in. I think that is probably the honest place to stop for now.